feel free to ask questions if you know, if you have questions. So what I want to do today is build on what we looked at last time, where we were starting to put together some pieces to analyze the groundwater flow. And we started with hydraulic head, and we'll move now into the flow law that describes the flow through groundwater. And I wanted to start out with a picture of groundwater flow. You know, I mean, groundwater flow occurs in subsurface, so kind of hard to come up with a picture. But this is kind of a cool shot here. I don't know if you can see everything really well, but there's maybe a little bit better. This is the Snake River here, and this is the wall of the canyon. You can see there's a tree there, and these are springs that are coming out, discharging onto the wall of the canyon, and then the waterfalls. You can see all along the canyon wall, they're discharging, and up here as well. And what happens is, in this place along the Snake River, there are basalt flows, big lava flows that form very low permeability units, and then they're stacked one on top of another, and there are permeable layers in between them. So the groundwater flows along these permeable layers and discharges here, and here it forms these springs. So kind of a cool shot. The weathering of the basalt also forms some fairly nice soils where the flows are older, and so there's agriculture up here on the highlands, and they use this fairly good aquifer for irrigation, and as a result, they don't have any springs anymore. They pull the groundwater out, and the springs have been cut off. So if there's a historical picture, but it's a pretty nice illustration of groundwater flow. So here's the stuff we're going to do. And to get started, I want to go and start with our definition of hydraulic head that we had last time, where for groundwater, we said that the total hydraulic head has an elevation head and a pressure head component. Okay, so if this is a column of water and it's open at the top, and it's just static, then we can apply this rule here. If we say that flow goes from high head to low head, high energy to low energy, and this is static, there's no flow, then the hydraulic head must be uniform in this whole column. So what we can do is plot these terms individually, and this would be Z, the vertical direction, and this is a datum here, a reference datum, and if we just plot Z as a function of Z, we can do that. So that would be a line that looks like this. It just has a slope of 1, right? Like Z versus Z. And if we plot the pressure head, then if we come across here, this is the surface of the water, so the pressure here is 0. And if we call that 0, then the pressure head is going to look like this. It's going to increase with depth. And then the total head is just adding these together. So if we add them together, what we get is so that's H, that's E, and that's E over gamma. Okay, so these components of the total head have a nice visual representation. And we see they add together and give us the total head in this column as equal to this value. It's the same everywhere. So there's no flow because there's no difference in the total head along that column. So that, I think, helps visualize what we mean by hydraulic head. But we can then use that to measure hydraulic head. And here's pretty much the same drawing. But what I'm going to do is say, okay, I want to find out what's happening right there. And I have a scale here. So I'm going to actually get some magnitudes of these different terms. So this is the start of my scale. So this is the datum. And the total hydraulic head right here is going to be measured up to that surface. So that's the total hydraulic head. Remember, the total hydraulic head in here is the same everywhere. So if we go up here, this is the total hydraulic head. It's rated like that. And then come across here, that's Z. And that's E over gamma. Okay, we can think of it just in terms of a length. You know, they have length scale. So the total hydraulic head is 4.5 meters. And this will be important later on. That 4.5 meters, we measure it here, but we're saying it applies right here. Okay, so the total hydraulic head, so H is equal to 4.5 meters. And the pressure head right here is equal to that length. And the elevation head is equal to that. So Z is equal to 1 meter. And the pressure head is just going to be that. And go and measure that. And I mean, it's going to be the difference between these two. So the pressure head is equal to 3.5 meters of head. Okay. Now, we could get the pressure and measure what the pressure is, because we could just multiply through by the unit weight, and the pressure at that place would be that times gamma. Gamma, remember, it has units of force per volume. We can also think of it as a pressure per unit length. So in SI units, it's 9810 pascals per meter gamma. So that's going to be around 10 kilopascals per meter. So this is going to be around 35 kilopascals pressure. Okay. All right. So that's all good, but we could also then apply this to the field. So that thing that I just sketched, we're gonna take that and put it here in the field. This is a cross section of aquifer. And here's our column filled with water. And there's the measurement point. But what I've done now is I've put a hole in this tube. And that hole connects the tube with the aquifer. Okay, so now the way to think about it is that the hydraulic head inside of this tube, this is now a sealed tube, goes up to the surface with a hole here connected to the aquifer. So within that tube, the hydraulic head is the same everywhere, and it's equal to this elevation. So there's the total hydraulic head at that point. It's 3 meters. Okay, so H equals 3 meters at that point. We can also get the pressure head and the elevation head. That's the elevation head at that point, and the pressure head is that. Okay. So we can keep going. The total head right here is about 4. And right here, it's say 3.5. And right here, it's, and this is important, it applies there, but it's this elevation. So that would be 3.2 meters. Okay, so we could also do pressure head and elevation head here. So what do you think? What's the pressure head and elevation at that point? Right here, elevation head is that, pressure head is that. So elevation head is the elevation above the datum. That's the elevation head. So what's the pressure head? Right? 0. So from the first day, remember the definition of the water table? I promised it would be on the exam. Or pressure is equal to 0. So yeah, pressure head equals 0 right here. That's the definition of the water table. So that means that at the water table, the total head equals the elevation. Okay, same here. Okay, that's the elevation head, or pressure is equal to 0. When we're here, that's the elevation, it's what, 1.5 or so, and then that's the pressure head. Okay, so we can measure the total head, pressure head, at these various points using this kind of technique. So these are called piezometers, and we're going to use these. Well, we're going to use, this is the technique that's used to measure hydraulic head and output. Okay, so we said that flow is going from high energy to low energy. Hydraulic head is energy density, so flow is going to go from high hydraulic head to low hydraulic head. So this is a little sketch. This is a tube filled with some kind of porous material. And these are our fluid-filled tubes sticking up. If this was an aquifer, these would be piezometers. If this is like an experimental thing, tube filled with sand, then these are often called manometers. Okay, I used to do an experiment in this class where I made a plexiglass tube and I had these things sticking up, and I did it in a lab where it was a lecture room, but it had a little sink, and I would hook it up and put the water in here and have water flow through this to show how this works. It almost always leaked, so it got to be kind of a pain and a mess. So I made this animation instead, but visualize that right now there's no flow, and the hydraulic head here is the same. So the hydraulic head in this thing is the same everywhere. Now, if we open a valve and hook it up to the water supply, we get a little bit of flow. Then what's going to happen is the head here at this end drops relative to that head. So we've got a head difference between these 2 points, delta H, and we've got a separation distance. So we take that ratio, and that ratio is the change in head over the distance. So that's the hydraulic head gradient, the difference in the hydraulic head over the distance. And I think just intuitively, you know, if we turn it up and have more flow, well, okay, actually now before we turn it up, we're going to plot it. So the first point, when there's no flow, plots right here. If we plot the flux as a function of the head gradient. And then we open the flow, and now we've got a little bit of flux. And this is the head gradient right here. And I'm plotting this as a function as flux. What we would actually measure would be the flow rate. I think we would probably, we could take this and put it into a bucket and time how long it takes to fill the bucket, get gallons per minute, and then we would divide by that area to get the flux. So that's what I'm plotting there. Okay, so we turn it up and increase the flux, and that's going to cause this head to drop relative to that head. So this distance stays the same, the head drop increases, so the gradient increases along with the flux. And we do that again, and we get a plot that looks like that. And what happens is if you do this at modest flows, where the term called the Reynolds number that governs or that describes the effect of turbulence, if you do that for low Reynolds numbers, you find that the flux is proportional to the hydraulic head gradient. Okay. So this has been known for quite a while. And the first person to recognize this and publish it was this guy, Henry Darcy. He was a hydraulic engineer in France back in the 1800s. So he was working in the early 1800s, and his paper was, I think, in 1853. So back in those days, the water supply situation was a lot different than it is today. Didn't have running water in your house. That was coming later. They had pipes, but it was difficult. It was complicated to make pipes, so you couldn't really have pipes going in your house. So what they would do is go outside of town and bring in water from aqueduct. At least that's what Darcy was doing at this place in Dijon where he was working. Some places they had wells and other things, but the way that they would get water distributed to people was with fountains in kind of in the middle of the town. So this is a fountain in Cincinnati where I used to live, and it's this ornate thing. There are these sculptures and the water spewing out. Here's a picture of the fountains in Dijon. So they're kind of decorative, but back in the day, in this day, they were the water supply. You would go and have your jug of water, and take it and put it underneath this thing and fill it up and take it home. So they didn't have water distribution systems. It was like carrying a jug of water. So basically then they had this centralized source of water. And they were beginning to realize that they had realized that you couldn't really just drink water out of the stream. That if you did that, there were going to be a lot of people getting sick and having big problems. So one of the earliest forms of water treatment was to just put the water through a filter made of sand. So they would take the water by aqueduct from outside of the city, and it would flow just by gravity. It was up in the mountains, so it would flow by gravity. And then they would put it through a sand bed, and that would filter out the colloids, the particles, and a lot of the bacteria too. So it took out a lot of the pathogenic bacteria. So with that fairly simple method of water treatment, they were able to make the water a lot healthier to drink. Okay, so you're starting with water outside of the city. You've got some high hydraulic head, and you're having it flow, and you want to have it go through the system and still have enough head to make a fountain, right? So if you're doing that, you got to figure out how much head you're going to lose by having it flow through a bed of sand. You want the sand there to clean the water, but you still want to have it go through the sand and be able to form a fountain. So Darcy did this experiment. This is his apparatus. And you can see he's bringing the water in here, going into the top, and it's coming down. And then there's a little spigot there, and he's filling up that box, and he would get the flow rate. These are manometers, so he could determine the water level here and here, and get the hydraulic head gradient by taking the difference in the water levels and the distance. Okay, so he figured out this relationship between the flow and the hydraulic head, and turns out he just did it experimentally. He just did a bunch of flows and measured a bunch of head gradients and found they were linearly related. It turns out it worked well, and it was really key to doing the calculations for flow through porous media. And it's so yeah, it became law. It's Darcy's law, and under laminar conditions, the flow rate is proportional to the head gradient. So it says the flux is equal to the head gradient times this factor called the hydraulic conductivity. So if we were to make a plot like that, flux function of head gradient, the hydraulic conductivity would be the slope of that line. So we can visualize that if we take this experiment that we just saw and we set it up. There's the head difference. So we calculate the head gradient and measure the flow. There's the head gradient. There's the flow. It's going through sand, so we get a high flow. So you can just imagine intuitively that if we did the same thing with the same head gradient here, except the tube now is filled with clay, we would have a much lower flow rate. Okay, so the flux is related to the head gradient. In this case, the head gradient is the same, but the flux is different, and that's accommodated by the different hydraulic conductivity. So porous media has hydraulic conductivity that's going to vary with the pore size, and that's going to control what the flux is for a given head gradient. Okay, so these are some synonyms for the flux of water, flux through a porous media. For this class, I'm always going to use the term volumetric flux. This is a term, the flux is used as a common term in physics, and there are many things that can flux. It's a flux in general is something going through a unit area in a unit of time. So volumetric flux is the volume, mass flux would be mass, energy flux can have a variety of things. So I'll always use this term, but you'll find in readings in the book, in the textbook, and if you're out practicing, there are other terms that are used. So here are a couple of them: specific discharge, Darcy velocity, and Darcy flux. Those are some of the common ones. They mean this. And so just as a heads up, I don't like these terms because, for example, this term, Darcy velocity, what we'll see is that the velocity and the flux are different. So the velocity of a particle of water is actually faster than the flux when it goes through porous media. So you don't want to be confusing velocity and flux. So I don't know. I just point this out so it kind of give you a heads up. But Darcy's law is going to be volumetric relating volumetric flux to the head gradient. There's volumetric flux, a volume going through a unit area. Okay, so Darcy's law is if you have the hydraulic head as a function of distance, then if you have hydraulic head that look like that, then the flow is going in that direction. So if you have flow in the x direction and it's proportional to the head gradient in the x direction. So there's the head gradient. The hydraulic conductivity for this class, if I'm writing capital K, that means hydraulic conductivity. Okay, so this is Darcy's law, but in order to get the flux going in the right direction, flux is a vector, so it has a direction to it. And in order to get it going in the right direction, we need to have a minus sign there, because that's a negative head gradient, and it's causing flux to go in a positive x direction. Okay, so this is the form of Darcy's law that you often see in one dimension. If we're just writing this as a scalar, so if we're determining the gradient as like a change in head over some change in length, and we multiply by hydraulic conductivity, then we don't need to use it to decide what the direction is. Then we don't need the minus sign. And you know, what we'll do in some cases is we'll say that we'll estimate what the hydraulic conductivity is by taking the hydraulic head gradient over here and getting this ratio. And you know, if you use this form, then you can end up having the hydraulic conductivity be negative. All right, but hydraulic conductivity is just a property of the material, and it doesn't really make sense for the hydraulic conductivity to be negative. So we would use this form of it and just have a positive number. We can also, though, have the hydraulic conductivity, or we can have the flux in different directions. We can do it in say, let's call it Q. We can do it in 2D. Okay, so the gradient in the x direction and the gradient in the y direction, we write it like that, and these should be partial derivatives. And we could also add in z for 3D. We'll do some 3D models later in the class, and this would be the form. We could write this in a compact way, like that, where that's the gradient operator. And we'll see in some cases, this would be how we would write it if hydraulic conductivity was uniform in every direction. Hydraulic conductivity will have a directional component to it. It can have a directional component. And so if it does, then you could write it like this, where this would be the hydraulic conductivity in the x direction, the y direction, and the z direction. So this would be the anisotropic case. So those are some forms. What we'll use mostly would be this 1D case or this, and sometimes I'll write it like that for 3D. Okay, so let's try doing this. Got some handouts here for you. Okay.
Was it? About the same. Oh, good.
Okay, so this problem is on the handout. The upper left. And let me just go through the first one. And then we'll let you folks do the second one on your own. Okay, so here's an example of this tube. And we've got manometers here. And we've got the measurement. Yeah. All right, let me do this. This is a little awkward position. Yeah. Yeah.
Just do it. There, this is just two different things.
Okay. Everybody have a handout? Okay. So let's do this example. So these are the two total hydraulic heads. So at H1, the total hydraulic head is 4 meters. So there's 4 meters. And at H2, it's 3 meters. So there's H2 is equal to 3 meters. H1 is equal to 4 meters. Okay, P2 or D is equal to 2 meters. So there's 2 meters. Go like this, there's 2 meters on that side. And there's 2 meters. Okay, L is 5 meters. And A, okay, we don't need those. Okay, so the pressure head at 1. So here's point 1. And the pressure head, we can do it. I kind of like to do it just visually at first. So this is the total head 4. Here's the elevation head. So this is the pressure head. And it looks like it's got to be 2 meters. And so that's 2 meters. And the pressure head here, there's total head of 3 meters. Pressure or Z is 2 meters. So this is 1 meter. And so the total hydraulic head gradient. Okay, so this is an important thing to remember. We have to get the total hydraulic head gradient using the total hydraulic head. We just calculated the pressure head, but don't use that for the total hydraulic head gradient. So the total hydraulic head gradient is the change of H, which would be just 4 minus 3 divided by 5 meters. So 1/5, 0.2. That's the total hydraulic head gradient. And it would be like, it's that divided by that, like the slope. Okay, so this is 0.2. And we can get the groundwater flux from Darcy's law. It's K times what is DH I didn't write it as DHDX because we're not really saying that X, although I mean we could we could say there's the x direction, in which case we could write this like so. And that's gonna be 0.2 times the hydraulic conductivity, which is 10⁻⁴ meters per second. So that's the height, that's the flux, groundwater. And the volumetric flow rate, that's gonna be Q times the area. So that's gonna be 0.2 times 10⁻⁴ meters per second times 0.1 meters squared. And so, yeah, that's just gonna be 0.2 times 10⁻⁵ meters per second. And if the units are meters cubed, right? Because here's meters, meters squared, so it's meters cubed per second. That's the volumetric rate. And draw an arrow showing the flow direction. So the way to do it is the flow is always going from high hydraulic head to low hydraulic head. So there's high hydraulic head, there's low. So that's the flow direction. Okay. All right, so that's the first example. So why don't you try this one? Did everybody break this down? Let's write it. Okay. All right. So go and work through this one, your own, and then we'll check it out. Okay. So let's take a look at this. So, let's see, what do you get for the pressure head? What do you got, what volts in it?
9 meters.
They're 9 meters. Anybody want to second that? Okay. And second, what about at 0.2?
1 meter.
What is it?
1 meter.
1?
1 meter.
Head gradient? For this side of the room?
0.6. 0.6.
0.6.
0.6.
The flux, 0.6 times that, right? Meter per second. And volumetric flow rate, gonna be that times 0.1. So what about the flow direction? Going up or going down? Going up, yep. So the highest hydraulic head here, there, so it's going up. All right. So let's do this one. And so this is pretty similar to what we just saw, but it's changed a little bit. The heads are now here and here. So the direction of flow is down, right? Highest hydraulic head is here. Lowest hydraulic head is there. So what I want to do is the pressure head at these 2 points. So there's total. And there's the pressure head here. And there's total. And there's the pressure head there. So what we said is going in that direction. So we can work out what these are. This is Z. This is P over gamma. P over gamma. And Z. All right, so do the subtraction. One of the things though that I wanted to point out is the flow here, as it always will be, is from high head to low head. So, or what about pressure head? Are we going from high pressure to low pressure? So the pressure head here is that. And the pressure head here downstream is this. So in this case, we're going from, the flow is going from high to low head, but it's going from low to high pressure. Okay, so this is an important point when we're calculating the flow and when we're trying to understand the flow, it's always the total hydraulic head and the pressure head. We can have flow that goes from high to low or low to high pressure. And this also works for an inclined case. And we have an inclined case, the procedure is the same, the total head, and if we're saying that this manometer applies right here, then we can get the pressure head and the elevation head there, and right here, it would be, there's the pressure head and the elevation head. Okay, and the total head gradient is that. The flow direction from high to low, so the flow direction is there. When we calculate the flux though, what we need to do is take the head difference between these 2 points and normalize it to the distance between them. So we would use that distance along the flow path to get the hydraulic head gradient. So there's numbers worked out. This is in the notes. If you should go and work through it yourself, make sure that everything is good. So can water flow from low to high pressure? Sure. It all depends on the geometry. All right, so those are some nice examples for tubes, but we can do the same thing in the field. This is going to be where the value is because we're interested in what happens in the field. So if we have these 2 piezometers, we can get the hydraulic head as these elevations. And so the hydraulic head gradient in the horizontal direction is going to be that distance, that change in head divided by the horizontal distance. So that's the horizontal head gradient between those 2. And we can also do this in the vertical direction. And this is where it becomes important to recognize that the hydraulic head, this hydraulic head, 3.2, applies here. This is, see the little dashes? That's what we'll see later is a well screen. Those are small slits in this pipe that allow water to flow through and connect this tube, this piezometer, with the aquifer. So the hydraulic head is 3.2 there. The hydraulic head here is 4.3. And the vertical hydraulic head gradient is that minus that divided by this distance. Okay, so we can get a vertical hydraulic head gradient with these 2. We can put all 3 together. Well, if we put the 2 of them together, then we get a horizontal component and a vertical component. And we would put those together and we would see that the gradient is inclined back, right? And if we have a flow system that looks like this, which, I sketched this out on the first day. And if the flow is perpendicular to the head gradient, then this is what the distribution of a hydraulic head would look like. And I've drawn, these are all right angles here. So this is the high hydraulic head, gets lower. So it goes like this, but what we see then is the hydraulic head right here is higher than it is down here. So we would have a vertical gradient and we would also have, it's also getting lower here. So we have a vertical gradient and a horizontal gradient that would give us this more complicated flow system. We can measure that with piezometers like that. Okay, so this ends up being a big deal because this is pretty easy to do. And what it means is we can get the hydraulic head gradient in the field vertically, horizontally, and spatially distributed. We can also measure the hydraulic conductivity. See how to do that, but that's feasible. So if we put them together with Darcy's law, we can get these head gradient measurements, combine it with hydraulic conductivity, and get the flux of the groundwater in aquifers. And the flux, that's how the groundwater is moving around through the aquifer. That's going to be kind of the cornerstone of our understanding of groundwater flow. Okay, and it'll be used in these techniques. All right. See you on Monday. Well, I'll see you on Wednesday, I guess. Got another day off. Hope everybody